The last part of looking at standard deviation is to talk about the empirical rule. Now, the empirical rule states that if a distribution is roughly bell-shaped, i.e. normal, that's the other word for that, then approximately 68% of the data will lie within 1 standard deviation of the mean, 95% will lie within 2 standard deviations of the mean, and 99.7% of the data will lie within 3 standard deviations of the mean. So what are we looking at? Well, I drew a picture right down here. So remember that the normal curve looks basically like this, and it's symmetric, right? So if you have your mean plus a standard deviation and mean minus a standard deviation, here's where the standard deviation is. It's called the inflection point. It's about where, how do I put this? Up here at the top of this curve, it's concave down. See how it's kind of bowl-shaped down? And over here on this right-hand edge or this left-hand edge, it's kind of bowl-shaped up, concave up. So the inflection point where the first standard deviation happens is the point where it switches from being concave down to concave up. In other words, if you were skiing down this, if this was a slope, this point would be where you were going your fastest, right? Okay, so that's where the first standard deviation always falls. So keep that in mind. So your first standard deviation will fall here, and that means that your first standard deviation over here is the same height. So you notice they're the same height and the same distance away. This is a perfect scale, right? So whatever the standard deviation is here, then the same distance is over here. Okay, so then if this is 68%, then this is 34% and 34% because it's perfectly symmetric. So half of the 68 is on the right and half of the 68 is on the left. Together, those two, that white section in the middle is 68%. All right, then what about the next sections? Well, notice that this is the same width from mu plus 1 sigma to mu plus 2 sigma as it was from mu to mu plus 1 sigma. In other words, one standard deviation and the next standard deviation have to have exactly the same width. All right, so whatever that width is, that's what they've got. And then it's 13.5% in that section. And then by the same token, 13.5% in this section. And notice they're identical because the graph is perfectly symmetric. And then this x-axis on the bottom has a scaling to it that is equal to your standard deviations. Okay, so if you add up these four numbers here, 13.5, 34, 34, and 13.5, you're going to get 95%. And then within 3 standard deviations, it's 99.7. That's adding in this next section, again, the same width as this other gray section and the same width as the white section. And if you add up these 6 numbers from 2.35 all the way up to 2.35, you're going to get 99.7. Now, of course, the entire curve has to have 100%. So that means that there's a 0.3% that's left outside of those 3 standard deviations. And then you split them up evenly, 0.15% over here on the right and 0.15% over here on the left. And that actually goes forever. It never stops. That's not the section between mu plus 3 sigma and mu plus 4 sigma. That's the section between mu plus 3 sigma and forever, right? It goes all the way to the right. Same thing over here. This 0.15% is actually mu minus 3 sigma to forever on the left. Okay, so let's see what else we can say. Oh, you can also do the same kind of idea with X bar and S because it's a generic rule. So it's going to work as long as your data set is normal. If your data set is not making this bell-shaped thing, then you've got other issues. If a single data value is beyond 2 standard deviations away from the mean of a symmetric distribution, it is considered unusual. So if you're past 2 standard deviations away in our course, we're going to consider you unusual, quote unquote. Or another way to put it, if the proportion of data that is in your region is less than 5%, that would be considered unusual. Of course, that's the same area we were talking about already, because if you're out here past 3 standard deviations, that only has a 0.15%, which is significantly less than 5%. Therefore, you'd consider it unusual. So unusual is this tail over here on the right or this tail over here on the left. And you can think of it either because it's a distance, more than 2 standard deviations, or you can think of it as a proportion, it's less than 5%. And that little idea there is going to come back in a big old way in Chapter 10. But we'll talk about it more then. Okay, so let's apply this idea to a problem. We have a survey conducted by the National Center for Health Statistics, and the sample mean height of women in the U.S. aged 20 to 29 was 64 inches with a sample standard deviation of 2.75 inches. Assume that the heights of women in the U.S. are normally distributed. So your first job is to construct by hand an accurate normal distribution with the parameters and percentages labeled. And there's more. You have to make it so that your scale, your percents, your numbers, everything's in there and they all matter. Okay, so you don't want to make scale in particular is one where, and shape is one where students mess up a lot. They'll make the first section really fat and then the next section really skinny and so on. And you don't want to do that. You want to make each section exactly the same distance. All right, so I'm going to go draw this with the computer and I'll be right back. All right, poof, there it is. So when you draw this, you have to draw a beautiful normal curve like this. Yes, it matters that you draw a good curve. Then you have to make sure that each section is evenly distributed. You want to draw your first standard deviation here at the inflection point, which is, it's not quite halfway to the bottom. So if you think of this as the top and this is the bottom of the curve, it's a little bit closer to the top, but not by much. There's the inflection point. And whatever this distance is, it's exactly the same distance here. Well, actually, we know what this distance is. It's 2.75. So the tick marks here, this is 2.75 for distance, then so is this. So 64 plus 2.75 gets you 66.75. 64 minus 2.75 gets you 61.25. Exactly the same distance. And you need to draw it as such. And then this next section has to be exactly the same distance again. So take 66.75 and you add 2.75 to it, you're going to get 69.5. That distance from left to right is exactly the same distance as 64 to 66.75 right here. That's because each section is one standard deviation. So you have to mark off on the x-axis, which is what this bottom line is. You have to mark off on the x-axis 2.75, then another 2.75, then another 2.75, with 64 as your center. And then you find the numbers by doing what I'm doing. I'm adding. 64 plus 2.75 gets you 66.75. Plus 2.75 more gets you 69.5. Plus 2.75 more gets you 72.25. And you can stop there. And then you do the same thing, but on the other direction. So 64 minus 2.75. 61.25 minus 2.75 gets you 58.5, minus 2.75 gets you 55.75. Then each width being the same and all the numbers marked off, then you have to put in the percentages. So this section over here is 0.15. It's actually that section to forever to the left, all the way over here. And then this bit right here is 2.35%, 13.5%, and so on. So you have to draw a normal curve, get your scale right. That means that each section is exactly the same width. Make it so your bars are here nice and vertical, right? Don't make them slanted like the Leaning Tower. Then you have to have these numbers on this horizontal axis perfect. Put the 64, which is your mean, in the middle, and then add or subtract away your standard deviations to find all the other numbers. And then you have to have your percents all in there and beautifully arranged. You probably won't have space to put the 2.35 or the 0.15. Well, you definitely won't have space for the 0.15 in the curve, so you just kind of arrow down to them. All right, now that we know how to draw this curve, let's find the percentage of women that are between 64 and 69.5. Okay, well, that's in here, right? So starting at 64 and working our way to 69.5, that's 34 plus 13.5. So let me write that out. That'd be 34% plus 13.5%, which makes a grand total of 47.5%. Done. All right, isn't it easy? Once you have the curve all beautifully drawn, figuring out this kind of answer is not too hard to do at all, at least at this stage. Of course, we know it's about that, right? It's not exactly that. And we'll learn about how to get a little bit more precise with it in Chapter 7. But for now, we'll just use this curve. So now what percentage of women are taller than 69.5? Well, 2.35 is taller, but so is the 0.15 because all the women over here on this tail, any woman that's taller than 72.25 inches falls over here. So together that makes 2.35% plus 0.15%, which would be 2.5%. Done with that. Now, the percentage of women that are taller than 64. Well, that requires almost no effort at all because the entire curve makes 100%, right? And 64 is the middle. So the percentage of women that are taller than 64 would be 50, right? So about 50%. Or if you like, you could add up all of these four numbers and you're going to get 50. Oops, that didn't work at all. There we go. Now, what percentage of women are between 61.25 and 72.25? All right, 61.25 is over here on the left, all the way up to 72.25, but stopping there. So we're going to add, let's see, it was 13.5% plus 34% plus 34%. Let me make sure I'm doing this right. 61.25. Oh, 34, sorry. 34, 34, 13 and a half. Got that backwards. So 34, 34, 34 for the first section, 34 for the next section, 13.5 for the next percent for the next section, and 2.35% for the last section, which would make 83.85%. And it's important you don't call that 84 because 84 would include the 0.15 over here on the tail, but we don't want to include that because that's where this little section ends. It starts over here at 61 and it ends over here at 72. Are any of the above results considered unusual? Yes. Taller than 69.5. Sorry, I have a new keyboard and I'm getting used to it. Taller than 16.5 inches would be unusual because the proportion is less than 5%. I wouldn't make a standard deviation argument here because I'm not really talking about standard deviations. I'm talking about percentages, right? So each of these answers is percentage, so I would use the unusual argument that's dealing with percentage rather than the one that's dealing with standard deviations. Although technically they go hand in hand. All right, we're all done with section 3.2. I'll see you back here for 3.3 when we'll discuss the weighted mean and finally being able to use the frequency list for one variable stats. See you then.